y'all. Today we're going to look at 4.9 on roots and zeros. This is the final section that we're going to look at, and if you notice that we've skipped section 7 and 8, as those are pre-calculus standards again that we'll look at if you take that course next year. So the objective for today is that you'll be able to determine the number and types of roots for a polynomial equation and define the zeros of a polynomial function. Our standard, continuing under AAPR3, being able to graph polynomials, identifying their zeros when suitable factorizations are available, and indicating their end behaviors. And we'll write a polynomial function of least degrees corresponding to a given graph. Now, the limit in Algebra 2 is degrees of 3 or less. We are going to look at some examples of higher degree functions, but that's just to get an idea of what's going to happen later on. The key in Algebra 2 is degree 3 or less. So let's talk about some definitions here that we need to know first. Zeros, factors, roots, and x-intercepts. Those four words we've been talking about as interchangeable throughout this unit. Remember that the zero is technically a part of a function. Remember that a zero is when we set that p of x equal to 0. A root is the solution of when we set it equal, right? So x equals something, that is the root, in other words, the solution. The factor c minus x, so if we were to factor something out of a polynomial, that becomes a piece. And then if c is a real number, then the order pair c comma 0 is an x-intercept of the graph, p of x. So remember, all four of these statements interrelate. They're not exactly the same thing, but they do relate to one another in a way. And so let's look at some examples of how we're going to use this. So the fundamental theorem of algebra states that every polynomial equation with degree greater than 0 has at least one root in a set of complex numbers. And there's a corollary to the fundamental theorem of algebra that will state that a polynomial degree of nth degrees, n being some number other than 0, will have n roots in the complex number system, including repeats. And again, that is part of the stuff that we'll talk about in pre-calculus next year. But for what we want to look at here, we want to look at some examples of how we can find the solutions, again, in the complex number system, and see how many roots and what they are. So in example 1a, we have x squared plus 2x minus 48 is equal to 0. We want to state the number and types of roots. Well, this is a quadratic, so we go back to our quadratic rules. Can we factor this? Can we solve this and figure out what x's are available to us? So if we try to factor this, remember our x puzzle, right? And so a times c is going to be negative 48. My b is positive 2. So what's going to multiply to negative 48 and add to positive 2? Well, when we go down our list of 48, 1 times 48, 2 times 24, 3 times 16, 4 times 12, and then we get to 6 times 8. And if I use 6 and 8, the 8 being positive, the 6 being negative, that added together will give me positive 2, and multiplied together, of course, will be the negative 48. So this will factor to x minus 6 times x plus 8 equals 0. Now remember, if our a was not 1, we could divide by a and do this method, or remember that we'd have to do factor by grouping. And that's what we talked about in the previous section about factoring methods. Make sure you use those factoring methods on other types of polynomials. Now in this case, we're going to set it equal, so we get x minus 6 is equal to 0, x plus 8 is equal to 0. So my two solutions here are both real. So I have two real roots. Now, being a quadratic, we could have also looked at the discriminant and not actually completely factored it. Because it wasn't, now it did ask to solve, so we need the solutions, right? But what are the types of solutions? They're real roots. And even in this case, they're actually rational roots. Okay? So let's look at example B. In example B, we're given solve y to the fourth minus 256 is equal to 0 and state the number and types of roots. Now, this is one where we could technically solve it for y, but there becomes some issues that come into play, and so we've got to be careful here. Now, this is a two-term polynomial, so we want to use some of our two-term polynomial methods, and one of those is the difference of squares. And so what square gives us y to the fourth? Well, y squared squared, right? Minus what squared gives us 256? Well, that's 16, right? 16 squared is 256. And so we're going to separate this out as a difference of squares. So y squared minus 16, y squared plus 16 is equal to 0. Let's look at these two pieces now because they can still be factored. And so y squared minus 16 is again a difference of squares. So that's going to factor. And so we're going to get y minus 4 times y plus 4. And then we'll bring down this other piece, the y squared plus 16. Because there is no formula for the sum of squares. We have a formula for difference of squares, but not sums. And so now I'm going to set each of these pieces equal to 0. So y minus 4 equals 0. Y plus 4 equals 0. Y squared plus 16 is equal to 0. Well, the first two are pretty easy. So y is going to be equal to 4. Y is going to be equal to negative 4. So I've got those two real roots so far. But remember what we said. The corollary of the fundamental theorem of algebra says that if I have a fourth degree polynomial, it better have how many roots? 4 in the complex numbers. I've only gotten 2 so far. The other 2 come from here. So we're going to solve this. Y squared, we're going to subtract the 16, so we get negative 16. And now we've got to take the square root of both sides. And remember that when you take a square root of something that was squared, this has to have the plus or minus in front of it. So we're going to get y is equal to positive or negative. Remember, if I got a negative inside the radical, that's going to come out as an I. And so I've got the I, but what's the square root of 16? It's 4. And so we get y is equal to positive or negative 4i. And so my 4 roots are negative 4, positive 4, and then positive or negative 4i. So that's my 4 roots. And so in this case, I have 2 real roots and 2 complex roots. Okay, that gives us our total of 4 complex numbered roots. 2 of them being in the real number system, 2 being, in this case, in the imaginary number system. Okay, so that's what we're looking at in this first 2 examples here. So as you notice, I've skipped example C from the notes because it's exactly like example B. So if you want to complete that one out and try it, great. Look for those solutions there. But I've moved on here to the corollary to the fundamental theorem of algebra. And like I said before, the corollary says this. A polynomial equation of degree n, being whatever the nth degree is, right, has exactly n roots in the set of complex numbers, including repeated roots. Okay, so we want to keep in mind that if a root repeats 3 times, it counts as 3 roots. It's just the same value. We won't list it 3 times in our final list of zeros or roots of the equation, but we have to know that it happened that many times. Okay, and so Descartes' rule of sign is what's going to help us with this next process. So we're going to let us have a function of nth degree, and it has real coefficients. The following 2 things are true then. The number of positive real zeros of the function is the same as the number of sign changes in the signs of the coefficients of the terms, or is less than that by an even number. And, part 2, the number of negative real zeros of the function is the same as the number of sign changes in the signs of the coefficients of the terms of p of negative x. That's a key point here. We're going to see that in an example. Or it's less than that by an even number. So again, if I find out that I have 5 sign changes in either case, it could be 5 or less than that by an even number. So I could do 5 minus 2 and get 3. Or I can do 5 minus 4 and get 1. So I would have to have at least 1 root on that side of 0. So either the positive side or the negative side, depending on which one that we have solved for here. So let's see what that looks like in example 2. State the possible number, positive real zeros, negative real zeros, and imaginary zeros of p of x is equal to negative x to the 6th plus 4x to the 3rd minus 2x squared minus x minus 1. So the first part of the Descartes' rule of sign is I look at the sign changes. And so when I go from the negative x to the 6th, that's my first sign. So we look to the next sign. It went from negative to positive. So that's my first sign change. And then here I went from positive to negative. So that's my second sign change. And then I went from negative to negative. That's not a sign change, so we don't count it. And then I went from negative to negative. That's not a sign change. So on the positive side, so positive real roots I could have 2, or any even numbered less than that. So I could have 2 or 0 positive real roots. Now we're going to look at it on the negative side. And so we're going to do p of negative x, which means I'm going to substitute out negative x, simplify any sign issues that I have, and then we'll look at counting what signs that we have. And so I get the opposite of negative x to the 6th plus 4 times negative x to the 3rd minus 2 times negative x squared minus negative x minus 1. We've got some signs to clean up here. Negative x to the 6th, that's going to be positive x to the 6th, because 6 negatives multiplied together is positive. But it still has the negative out front, and so we will leave the negative that was there. Negative x to the 3rd, that's a negative times a negative times a negative, so that's a negative. So that's going to change when I multiply to this positive 4. So it's going to be minus 4x to the 3rd. Negative x squared, our next term, negative times negative is positive, so it's not going to change the sign of the negative 2 that's in front. So I'm going to have minus 2x squared. Negative times negative is a positive, so that's positive x, and then I have the negative 1 at the end. So p of negative x is negative x to the 6th minus 4x cubed minus 2x squared plus x minus 1. So now we count the sign changes here. Negative to negative, don't count. Negative to negative, still not counting. Negative to positive, that's 1. Positive to negative, that's 2. So this will have, at most, how many negative real zeros? Or negative real roots? It will have 2. Or it can have an even number subtracted from it. So 2 minus 2 would give us 0. Now, we're going to set up a table, and this is what Descartes' rule of signs allows us to do, is to see how many roots this will have. And so we're going to have positive, negative, imaginary, or complex, and then the total. The total will never change in this, because the total is based on the degree. Go back to the corollary, that if I have an nth degree polynomial, I have to have n roots, including repeats, in the complex number system. And so, no matter what, the degree of this polynomial was 6, so my total will always be 6, no matter what pair I do. And so I've got to make sure everything adds up. And so now we're going to combine these together in all the different pairings. So 2 positive, 2 negative, that's only 4 roots. Well, the other roots are going to be imaginary roots, and they're always going to come in pairs anyways. That's why we have to subtract by 2. And we'll get to that more in pre-calculus. But understand that imaginary roots always come in pairs. And so 2 plus 2 is 4. I need to get to 6, so that's 2. All right, I'm going to take 2 positive with 0 negative, so 2 positive with 0 negative. That's only 2 roots. I got to get to 6, so that leaves me with 4 imaginary roots. Now I'm going to take the 0 and match it with the 2, so I get 0 positive, 2 negative. So 0 plus 2 is 2, so I still need 4 imaginary roots. And then my final case, 0 positive roots, 0 negative roots. And so 0 positive, 0 negative means that all of my roots are imaginary or complex. So I get 6. So these are the possible cases of positive real roots, negative real roots, and imaginary or complex roots. And again, that total will always be totaling to the degree of the function. That's what we're looking at with Descartes' rule of sign. So let's look at example B and see what we're doing there. So in example B, we've got p of x is equal to x to the 6th minus x cubed plus x squared plus x plus 3. So I want you to pause the video and I want you to figure out how many positive real zeros that we're going to have in this problem. So let's just do positive first. Pause the video here and let's look at those. All right, so let's see what you got. So with positive, remember we're going to start with the first sign. So that's positive to a negative, that's 1. Negative to positive, that's 2. Positive to positive, positive to positive. So we get 2. So the positive real roots or real zeros, I could have 2, or we could drop down minus 2 and get 0. Now let's set up for the p of negative x. And I'm going to walk through this again with y'all. So p of negative x. Remember, we're going to plug in negative x for each x that we see. We'll deal with our exponents, and then we'll deal with the multiplication because that's the order of operations. And so plus the negative x and plus the 3. So dealing with our signs, remember, if it's to an even power, a negative to an even power comes out positive. A negative to an odd power comes out negative. So we're going to get x to the 6th. This will come out negative, but a negative times a negative is a positive x cubed. Negative squared is going to give us positive, so positive x squared minus the x and plus the 3. And so let's look at our sign changes there. Positive, positive, not a change. Positive, positive, not a change. Positive, negative, that's our first change. Negative, positive is our second change. So how many negative real roots do we have? It could be 2 or it could be 0 because 2 minus 2. And so we set up our table. So I want you to, again, take a second, pause this video here, and write out the table, remembering that the total of any line is going to be equal to the degree of the polynomial. And in this case, that was 6. I'm going to tell you, you're going to get 4 cases in this. So try out that example. All right, so let's look at these roots. We're going to start again with our pairing, so 2 and 2. So 2 positive, 2 negative. I got to get to 6, so 2 plus 2 is 4, so that leaves me with 2 more to get to 6. So 2 of these roots would have to be imaginary or complex. So now we're going to pair the 2 with the 0. So I get 2 and the 0, so 2 plus 0 is 2. So that leaves me 4 to get to 6. 0 with the 2, so 0 and 2. 0 and 2 again is 2, so that leaves me 4 to get to 6. And finally, the 0 with the 0. 0, 0, meaning that all the roots would have to be imaginary. Now, this is just the possible cases. Descartes' rule doesn't say that when you get one of these lines, it will be that line. You've got to dig a little deeper, and that's, again, part of the pre-calculus side of finding those roots. We are going to do a little bit of that in this section, but understand that Descartes' rule of signs allows us to know the possibilities that are part of this section. All right, so let's go on and look at the next example. So in this example, we're going to use synthetic substitution to find zeros. Now, we looked at synthetic substitution the other day when we looked at using it to just find remainders. But here's the thing, is when the remainder becomes 0 in synthetic division, that means the r value that we used is a root or 0 of the function. And so we're going to use synthetic division here. And so we're going to do 1, -1, 2, and 4. Now, Descartes' rule of signs says that we have to have so many zeros, right? And so we look at Descartes' rule of signs, 1, 2 didn't change, right? So 2 positive or 0. And then if I look at the negative side, this one would change, this stays, change state, right? So we'd have negative x cubed minus x squared minus 2x plus 4. And so negative, negative, that changes, that's 1. 1, negative, real 0. So what are my cases in the table? Positive, negative, imaginary, and total. Well, the total would be at 3, right? So whatever I've got is 3. And so positive, I could have 2 with my 1 negative. So that's a total of 3, so I have no imaginary. Or, remember, I could have 2 or 0 here. So 0 with 1 negative, which means I have 2 imaginary, which gets me to 3. There's no other pairings because those two have paired both with the 1. And the 1 can't change from anything because it can't go to 0 because 0 is not even numbered away from the original. So in this case, I'm either going to end up with 2 positive and 1 negative, or 1 negative and 2 imaginary, meaning that I'm not going to see them cross the x-axis. And so when we look at the graph of this, we look at the graph, and we see the graph, we see one value here. We see that the case is 0 positive, 1 negative, and 2 imaginary. And so we want to try the value here. We want to see, does this go through perfectly at this value? So we look at -1. So remember, the 1 will drop straight through. 1 times -1 is -1. -1 gives us -2. That'll multiply to a +2. Positive 2 and positive 2 gives us positive 4. And negative 1 and positive 4 gives us negative 4, giving us 0. If we get 0 here, then what that means is this is now factored down to x squared minus 2x plus 4, because our remainder was 0. And so then I can take this piece and factor or quadratic formula or something to get the other zeros. We got to get the imaginary zeros that are in this case. So we set this part equal to 0. Again, it won't factor, like if I try to do AC method, 4 on top, negative 2 on the bottom, nothing's going to pair up. I could try to complete the square here. I could do x squared minus 2x. Remember, we're going to put our plus blank on both sides. And in this case, I'm going to subtract the 4 across because we want it set with that c to the other side. And so what number is going to plug into the blank? Remember, it's half of the b squared. So half of negative 2 is negative 1. Square that, you get positive 1. So we're going to get 1 and 1. And so this is going to come out to x minus 1 squared is equal to negative 4 plus 1, so that's negative 3. We take the square root of both sides. Don't forget your plus or minus. So x minus 1 is equal to positive negative I root 3. Remember, the negative inside the radical comes out as an I. Square root of 3 does not simplify. So these are my other two roots. Well, not yet, right? We got one more step here. We got to deal with the minus 1. So x, we got to add the 1. And so x is equal to 1 plus or minus I root 3. So that's my two complex roots. 1 plus I root 3 and 1 minus I root 3. Those are our two roots. And so our three roots, we confirmed negative 1, but we also confirmed 1 plus or minus I root 3. And so we would write it like such. So that's what we're doing there. So again, if we can get the real ones off the graph, or we can get them proving it through synthetic division, that's what we want to do. And then we're able to find the others using our factoring methods or other methods of solving that we've talked about in Unit 3 and Unit 4. So in example B here, we've got x cubed minus 3x squared minus 2x plus 4. And again, we're going to look at the graph first, and we're going to see that we have 1, 2, and 3, right? Descartes' rule of signs would show us that that's one of our possibilities, that we're going to have 2 positive and 1 negative in this case. The other possibility would be 0 and 1, and then 2 imaginary. But we get 2 positive, 1 negative here. And we want to look at, did any of these cross at a nice value? This one looks like it does. So let's try the synthetic at 1. And so 1, negative 3, negative 2, and 4. Remember, the 1's going to drop through, so we get 1. So that gives us 1, which gives us negative 2. Gives us negative 2, which is negative 4. And negative 4 subtracted or added from the 4 will give us 0. And so this will become x squared minus 2x minus 4. Because again, this is our remainder. The remainder came out to 0. It proves that 1 is a 0 of the function. So like the previous problem, we're going to take this now remaining piece, this quadratic, and we want to use one of our methods to be able to solve this. And so again, we could complete the square, we could use the quadratic formula, whatever method is going to work best for you to find these final zeros of this function. And so I'm going to complete the square again, leaving my blank on both sides. I'm adding the 4 across in this case. And so b over 2, that would be negative 1. And negative 1 squared is positive 1. And so we get x minus 1 squared is equal to 5. Take the square root of both sides. Square root, don't forget your plus or minus. We get x minus 1 is equal to positive or negative square root of 5. That is a real number piece. It is irrational, but it is real. And so we're going to add 1 to both sides. And so we get that x is equal to 1 plus or minus the square root of 5. And so my three roots in this case, the 1 that we found here, and 1 plus or minus the square root of 5. And what we see, this actually has a little bit of symmetry to it. The point of symmetry is actually this vertex here, or that x-intercept there, and that's what we're looking at, okay? So now, you're not always going to have points of symmetry. It's just a fun little piece of this one because that's where it came out. So let's look at the next theorem below, the irrational roots and the complex conjugates theorem. So irrational roots and complex conjugates basically say the same thing. It's that they're always going to come in pairs, And if I have a irrational part, it's a plus the square root of b, and a minus the square root of b will also be a piece of it. And if we have complex conjugates, if we have a plus bi, we also have a minus bi. And so those two solutions will always be in pairs. And that's why I told you that imaginaries are always in pairs, because of the complex conjugate theorem. Now, let's see what that does in our final example here. We want to use synthetic division and write a polynomial function of least degree with the given coefficients, which include 4 and 5 minus the square root of 3. So we're actually working backwards from what we did in example 3. In example 3, we were given the graph, find all the zeros. In this example, we're trying to build the function back with integer coefficients. So watch what happens here. Remember that each factor is x minus r, right? And so the first one, x minus the 4. But then I've got this piece, and the two theorems that we just talked about, irrational roots and complex conjugates, this is an irrational root, so I'm going to get a pair. I'm going to get 5 minus the square root of 3, but I'm also going to add to my list 5 plus the square root of 3. That's the conjugate. When you see that sign change in front of the irrational or the imaginary term, that's the conjugate. And so I'm going to get x minus 5 minus root 3. And I'm going to put this little piece in parentheses, and we'll talk about that in a second. And then my other piece, x minus 5 plus the square root of 3. Now, I've done that intentionally, and you're going to see why in the next step. I'm going to multiply these two parts in red together first, deal with the part in green second, because that's the easy part. So, FOIL, right? Everything in the first has to multiply to everything in the second. And I'm going to show you why we do it in this order. We're actually going to redo our parentheses. First, we want to redo our parentheses around this and around this instead. Because remember, associative property, I can group however I want. And so if I do x minus 5 times x minus 5, I get x minus 5 squared. And then multiply that to the plus 3. So I get plus the square root of 3 times x minus 5. And then the back side, the negative square root of 3 times the x minus 5. And then negative square root of 3 times positive square root of 3 will be negative 3. So all of that goes in one big bracket at the moment. We're going to simplify that. This squaring out, so x squared, this multiplied together times by 2, so that's negative 10x. Square the back with a positive, plus 25. Positive 3, square root of 3, x minus 5, and negative 3, square root of x minus 5. That all cancels. We get a minus 3 at the back. Close the parenthesis. So x squared minus 10x plus 22. We still have this x minus 4 that's been hanging out front. And so now we're going to finally deal with it and multiply it out. And so we're going to multiply in, and again, you could use a box method here if you want to organize your work a little better here to make sure your stuff is multiplied together right. And so we're going to get x cubed minus 10x squared plus 22x minus 88 plus 40x and negative 4x squared. Combine the like terms, our final answer, x cubed minus 14x squared plus 62x and minus 88. This would be the function, and we would call it f of x or whatever function name they told us to use. But this would be the function that we're looking at in the end that has these as zeros with all integer coefficients. Now again, we can multiply by 2. It would be the same thing. We'd have the same integer coefficient, the same zeros of the function. So that's what we're looking at in this section. Again, there's a lot here. I know this is a long video, but there's a lot in this section that we need to look at. So make sure you fill out that Google form. Make sure you have taken your notes. And if you have any questions, make sure you fill it out that way. And I will catch y'all next time.